entitled Private Sampling with Identifiable Cheaters. And César is giving the talk, right? So, the stage is yours.
So, hi everyone, I'm César, and I will present my work on private sampling with identifiable cheaters, which is joint work with Florian Hahn, Andreas Peter, and Jan Roman. Let me start with a motivation example, with an example to motivate our work. So consider private aggregation, in which we have a set of parties, a set of n parties. Each party has a vector VU, and no party is trusted with the data of other users. And the goal is to estimate the aggregation of these vectors while satisfying differential privacy. So this is a key primitive for federated learning and can be used for other privacy-preserving machine learning computations. So I'm not going to get into the details of differential privacy because it's not that important, but I will show you the sketch of how you can do this. So basically, in this example, what users are going to do is to sample. Each one is going to sample one private sample according to a distribution to satisfy differential privacy, and then they will add it to its private vector and will aggregate it to get a noisy estimate. So you can do this either in the clear, or you can use some kind of secure aggregation primitive or secret sharing, so you can get like some accurate estimates. So the problem with this is that if you are in the presence of malicious users can either poison their private vector or poison their noise. While methods exist in which you can verify the consistency of your private vector, for example, zero knowledge range proofs, verifying that a private sample is drawn correctly from a prescribed distribution is a less explored problem. So this is our problem. So basically, we study secure randomization for privacy-preserving protocols. So the setting is n parties, and an adversary that is a static set of colluding malicious users, and a publicly known distribution D. And we want to generate verifiable noise samples. So basically, we want to run a multi-party protocol to generate a number eta, such that if at least one user is honest, this eta will be unknown for most of the parties, but all parties will be can verify that it's sampled from the correct distribution. I want to provide two flavors of this verifiable sample. So we want to provide private samples in which only one party knows eta, and hidden samples in which nobody knows this because it's a secret share among all parties. So our contributions are the following. So we propose protocols for private samples for the Gaussian, Laplacian, and arbitrary distributions, and hidden samples for Gaussian and Laplacian distribution. Then we evaluate Gaussian private samples, and we show that we outperform private work. And while doing so, we propose novel techniques to prove non-polynomial finite precision relations in zero knowledge, which is kind of interesting and has independent interest. And we prove malicious security with identifiable abort. So our protocols either finish correctly or abort detecting a cheater. So let's start with private samples. So the tools that we're going to use is a public bulletin board. So parties can post messages on this shared board. And then we're going to use zero knowledge proofs. So basically, we're going to use compressed sigma protocols. I am going to make them non-interactively using the Fiat-Shamir heuristic. So this is the technique is kind of similar to bulletproofs. See if someone knows this kind of zero knowledge proofs. So the key idea is that you can prove arithmetic circuits of private values in zero knowledge. So let's start with the uniform distribution. So what can you do? So basically, what you can do in the uniform distribution, so if you are in a range 0m, so you can do is that this P1, which will know the sample, will commit to a private value X that is sampled randomly from 0M. Then all parties will jointly generate a number Y in the range 0M. These two values will be posted in the public bulletin board. Then P1 will sample eta and will prove that eta is the modular sum of these two numbers in zero knowledge. So then this sample is only known by P1, but anyone can know that this is uniformly distributed. So then for any distribution, what you can do is to build up on these uniform protocols. So basically, you can use the uniform protocol to generate private seeds and then make P1 to prove that that eta is a transformation of these private seeds in zero knowledge. So if you, for any distribution that you can compute the inverse CDF, so this transformation is actually, for any distribution, is the inverse cumulative distribution function, if you can compute it. But there are also some other specialized techniques, for example, for the Gaussian distribution. And for these transformations, we propose, we create like a bottom-up set of building blocks from very basic finite precision operations to more mathematical computations. So this is, we can compute logarithms, trigonometric functions, and other functions, which are kind of very interesting if you want to prove relations in zero knowledge. And we avoid methods such as table lookups and splines, which are quite common, so we can obtain nice properties such as no pre-processing, few comparisons, and customizable precision in our approximations. So now you can obtain, if you vectorize this protocol, you can get private aggregation with an unbiased estimate. However, if you have a set of colluding malicious users, they will still know their own noise terms. So basically, honest users will have to add more noise to compensate according to the upper bound on the estimation of malicious users, which will make the estimation more noisy. So basically, this is the motivation for the hidden samples. So here, eta is secret shared among all parties. Nobody knows it. And in addition to our current tools, we are going to use arithmetic secret sharing, which allows to compute arithmetic circuits from secret shared values. Again, so this the methodology is quite similar to the private sample case. So here, each party draws one number, one random number, and you can see that this is already a hidden draw of eta for the uniform distribution because the modular sum is uniformly distributed. So for other D, what we do is we plug our approximation circuits in secret sharing. So we generate uniform seeds and we plug this transformation that we do. So then you can have an unbiased output with optimal amount of noise as if you would have done it with a trusted party. And you have no accuracy degradation even if n-1 user collude, which can be some possible attack in this setting. So basically, we evaluate private Gaussian samples. And we evaluate it so basically the Gaussian distribution is widely used in distributed differential privacy. But the prior work is kind of like the technique that is being used is kind of very old and it has not improved. So what they do is basically use the central limit theorem approach, in which for each sample you generate a lot of uniform seeds and then you average them to approximate the Gaussian. So we propose methods that require only one seed per sample. So we propose methods based on the inversion method. So basically, one of the challenges here is that the inverse CDF of a Gaussian has no closed form. You have to approximate it. So we propose methods that approximate it with series and with rational functions. Then we propose other more specialized methods, which are the Box-Muller method, which requires computations such as logarithms, square roots, and trigonometric functions. Then we propose also an optimization which avoids trigonometric functions using rejection sampling. Then we compare this for different precision parameters. So basically, we compare the statistical quality of an ideal Gaussian, is the mean square error to an ideal Gaussian, and we compare the cryptographic cost of our CKP transformations. So we can see that all, basically the CLT is the one that goes more on diagonal, that from the bottom up to the, from the top left to the bottom right. And we can see that all methods, as soon as you require a certain statistical quality, perform much better. So basically, the best one that performs is are the Box-Muller and the Polar method, but also the inversion method is also in the same order of complexity. Here we propose also one method that is just a point because it has not customizable precision, so the inversion method with rational approximations is just a point there. But still, okay, this CLT is good if you need low quality samples, so it's still kind of fast. So that's all. Thanks for listening, and you can find me in the poster session and ask questions here.
Yeah, thanks a lot for the talk. Are there any questions? So in Zulip, nothing has been uploaded, nothing has been posted. Yeah, okay.
So very quickly, why do you have such a high mean squared error for a few number of samples? Based on your experiments, it feels like you need to reach a certain number of samples to make it worth it.
So for a few number of samples, so basically this is mean square error. Can you repeat the question? Sorry.
Yes. Why such a high mean squared error when you go beyond 25 group elements on the left-hand side?
So this is basically this is the group. This is like the communication cost. So we have tested this with all the methods, and we see that this. So 10 to the so for 25 elements, you have like 10 to the -4. So do you think that this is like still like too costly?
Or rather, right before, for 20 elements, it goes very, very high.
Before with 20 elements, but okay.
Oh, we can discuss it after.
No, but it's okay. So you're saying in the curves that are more vertical? Yeah. So there's like a huge overhead at the beginning on the approximation. So you have to set up. You have a lot of computation that is just for the this becomes is like the first constant at the beginning.
Okay, but that constant does involve a lot of error, not only a lot of communication.
So basically, it just you have like a base amount of computations before you can start reaching some nice acceptable accuracy. Yeah, I understood your question now. Yeah.
Thank you.
Okay, so we have time for a very short question, if you have one. I would have one. I mean, you were distinguishing between this private sample and hidden sample.
Yes.
And you motivated it with differential privacy application. And I totally buy it. I was just wondering for the private sample scenario where one party knows the noise. Then in the differential privacy scenario, I mean, this would only work if this one party is trusted and is not collaborating with the one who is doing the analysis. So my question is, do you see any applications for the private sample solution?
So the private samples are still like much more scalable to a large number of parties because the other ones is multi-party computation, which will make the cost, like the overhead, if you have a lot of parties, like quite high.
Okay, so in principle you have a stronger trust model, but you gain efficiency in principle.
Yeah, and you can, if you still have honest parties, like you can still reach some.
Okay, then I would say thanks a lot and thanks to speaker N.